Okay, so this is part 2, but as often happens, I realized there's something I didn't say in the previous video. So there's 2 things. When I did the demonstration of photoelectric effect, there is another tuning knob, which is to choose a metal. I worked with zinc. It was a simulation of zinc. Now you can go to PhET and you can try a different metal. Now different metals have a different work function. Okay, different metals require different amount of energy to liberate an electron. And then you will see that the critical frequency at which electrons start to come out will be different for different metals. So that's another control knob that I forgot to play with during the simulation, but I said it in words. And part 2, I want to emphasize that this right here is the energy per light quantum, energy per photon. I even says energy of each photon is proportional to frequency, right? So this is energy per single photon, right? So the idea is, okay, light comes in this discrete entities, call them whatever you want, but the point is that these entities have an energy that's proportional to the frequency. Okay, so now I want to talk about something related, something that built upon Einstein's idea, and this is Compton effect. So this is, I guess, Compton. Is it called Compton effect or Compton's effect? It's called Compton effect. And this is named after Arthur Compton. I think Beta had a few anecdotes about Compton. So now look, I expect you to know certain classic experiments of modern physics. Well, what experiments did we mention so far? We talked about Michelson-Morley experiment, which indicated the absence of ether, or at least that it's very hard, that there are no obvious signs of ether. That's really the upshot of the outcome of that experiment. Then we, so that's related to relativity. Now we just discussed photoelectric effect. Now on photoelectric effect, I want to say this. I actually went to campus and we have that demo, and I filmed that demo. So watch for that video. Okay. So in any case, the second very simple smoking gun that led to us reconsidering classical physics is the photoelectric effect. And the upshot of that is that it demonstrated that light cannot be thought of as a wave. It showed some cracks in our understanding of light as just a wave. Okay, and Einstein said, well, let's think of it as a particle. And now I would like to mention briefly a third classic experiment called the Compton experiment, or the Compton effect, which showed another crack in the wave description of light. In fact, more than just showed a crack in the wave description of light, it actually solidified the idea that light really should be thought of as particles. Okay, so what is this experiment about? It's about scattering of light by an electron. By an electron. Okay, so if we had two particles, if we had scattering of an electron by an electron, well, you would have particle 1 and maybe particle 2, and this particle goes like this, and this particle would go like that, right? So that's what you would expect with particles, right? So this is two particles, pebble against pebble, electron against electron, whatever. Well, the point of this experiment is that it appears that light scatters off of electrons as if it were a particle, okay? Now, what do we expect classically? Again, why is it that this demonstrates that light behaves as a particle? Can you have a scattering of wave off of a particle? Can I put a wooden log in the ocean waves I can think of waves scattering off of objects, of scattering off of particles, right? But the way in which it scatters would be different. So classically, we expect an incoming electromagnetic wave. What happens? So here comes the electromagnetic wave. Here's an electron. You, Phys 3 aficionados, you tell me what would happen. Classically, it's a wave of electric and magnetic field. And you would expect the electron to respond to that field. Now the field is periodic, so the electron would do something like that. So that wave, it shakes the electron at its frequency. Now, when electron is shaking, it's accelerating. And accelerating charges emit radiation. So in other words, the shaking electron would emit another electromagnetic wave. But here's the kicker, that the frequency of that re-radiated wave produced by the shaking electron would have the same frequency as the incoming wave. Now, some of it would scatter back, but the important point is that it would have the same frequency. Okay, that's the classical prediction. What Compton found instead is that, yes, there is light scattered by an electron, but this scattered light has different frequencies. Okay, and the frequency or wavelength depends on the scattering angle. So now let's dive into it. So, okay, so this is, so you have a wave against a particle. Okay, here's a wave, here's a particle, and the wave, you know, here's the incoming wave and here's the outgoing wave, right? And so the wave would scatter, okay? So lambda incoming and lambda outgoing. So incoming, outgoing. Imagine if this is like a rubber ducky on the waves. Okay, well, the point is that classically, i.e. waves, wave picture of light, we expect lambda prime to be equal to lambda. Compton showed that lambda prime is not equal to lambda, but not just that. He showed specifically how lambda prime differs from lambda depending on the angle, okay? So, and then he was able to explain that result by taking seriously incoming light as a bunch of particles, photons, and treat it like a particle-particle collision. So how do you do that? Okay, so how do you do that? So take particle description of light seriously and treat this as a particle-particle collision. Now, how do we understand collisions, right? If I give you incoming velocities, I'm asking for outgoing velocities, what do? Exactly, you conserve energy and momentum. So you need some kind of a formula for momentum, right? So classically, it's momentum is mv and kinetic energy is 1/2 mv squared. In relativity, momentum is gamma mv and energy is gamma mc squared. In any case, the formulas are different, but you still apply conservation, and that conservation allows you to relate outcome, the properties of outgoing, the scattered particles, to the incoming particles. Now, if we take Einstein's idea seriously, then if we take it as a particle seriously, well, what we have to do is we have to use the energy of that particle, which is given by E equals HF. That's what Einstein proposed. And what about the momentum? Well, so okay, so I have to open a little box. Let's go back to relativity. This is where relativity is actually important. Recall Recall that in relativity, we have the following relationship: E equals mc squared over 1 minus u squared over c squared, okay? Which is okay for massive particles, but what about for light? Light travels at the speed of light, okay? So it suggests that for massive particles, to go at the speed of light requires infinite amount of energy, but it also suggests that it's not, that this formula might not work if a particle is massless. Now, before relativity, no one in their right mind would think of such a thing, massless particle. But you see now that if particle is massless, the numerator is 0, okay? And it would suggest 0 energy unless the particle also goes at the speed of light. It suggests that massless particles go at the speed of light, and then this formula is useless. Okay, so if a particle is massless, then both the numerator and denominator is 0. Okay, and you should interpret it like this, that massless particles perhaps can exist as long as they travel at the speed of light. That's what this formula suggests. Well, that's interesting. So it's almost consistent with the idea of light being particles, massless particles. But in any case, one might say, well, fine, this is all good, but what is the formula for energy of such massless particles? And then relativity does not offer you an answer. You see, this idea equals HF, it's a separate idea. It's beyond relativity. It's a separate sort of branch of studies, right? But what relativity does tell you, it does suggest how energy and momentum can be related, because recall that you have E squared equals P squared C squared minus, no, E minus P squared C squared, E squared minus P squared C squared equals M squared C to the 4th. And so then if M equals 0, this suggests that E equals PC. Again, relativity says, well, it's okay. You could have massless particles. It doesn't give you a specific formula for energy of such particles. That requires additional piece of physics, like quantum mechanics equals HF. But it suggests that such particles should be possible as long as they travel at the speed of light. And moreover, it actually gives you it suggests how the energy and momentum would be related. Okay, so then now we can use that here. We can say, well, P equals E over C. That comes from relativity. But we do know what E is. It's HF. That came from trying to understand photoelectric effect, and also from Planck's ideas. So let's substitute that HF over C, which is H over lambda. Remember, so lambda equals C over F. I always remember lambda times F equals C, so F over C is 1 over lambda. Okay, that's Phys2 material. Good, so now we have, photon. I'm still going to represent it like as a wavy line, but it's a photon. Now we have a photon, okay, with momentum equals H over lambda, energy equals H times F, and then you have an electron sitting here. So this is before, and then after, well, after you have something else, right? So after you have, so this is angle theta, this is angle phi. You have electron. It has a momentum equals H over lambda prime, and it has energy equals H times F prime. Now, lambda prime F prime equals C. And the electron has a momentum equals gamma mu, right? I'm going to use the letter U like in your textbook. And the energy equals gamma mc squared. Okay, so we have formulas for energy and momenta. And so now we're just going to treat it like a particle-particle collision with these funny formulas for momentum and energy of a massless particle, okay? Now, your textbook actually goes through the derivation. So apply energy and momentum conservation, okay? And if we do that, so that's equations, let me see. So I think that's done in the book. Okay, so apply, but the key is you just grind through the math, you apply energy and momentum conservation, and when all is said and done, result, I'm just going to present the result. It gives the following interesting formula for the difference in the incoming and outgoing photon wavelength. It's h over mass of an electron times c 1 minus cosine of theta. You see, so depending on where you place the probe, right? So you can place the probe here at this angle, you will see one wavelength. If you place the probe here at this angle, you will see a different wavelength. So that's what this formula says, okay? So observed wavelength of the scattered light depends on the theta, the angle of the probe that's collecting light. Okay. And guess what? They went to the lab and they found exactly this relationship. What's the moral of this? The moral is that, yes, you should take light as a particle seriously, although it has these funny formulas that give the momentum and the energy of light. Well, why are they funny? They're funny because they still have the wave information in them. So this is, again, this is a little strange. It says, well, on the one hand, yes, of course, take that seriously as a particle. But on the other hand, you still have information about the wave behavior, right? Frequency and the wavelength. Okay. So the important point here is that the wavelength, the scattered wavelength, differs from the incoming wave. And that cannot be explained classically by a classical wave. The scattered wavelength, by the way, is always greater. And that kind of makes sense because larger wavelength means smaller frequency. Well, why would the frequency of the scattered photon be smaller? Well, frequency is related to its energy. And since it gave some of the energy to the electron, which now has kinetic energy, the photon must have lost some energy. Just one comment. This thing right here, okay, it has units of 1 over meters, right? So the quantity h over m electron c is called Compton wavelength. Well, in this case, it's Compton wavelength of an electron, because it's electrons, mass of the electron that sits in there. Now, you can talk about Compton wavelength of any particle. So Compton wavelength of a particle is equal to the wavelength of a photon whose energy is the same as the mass energy of that particle. So in other words, you take mc squared and you equate that to hc over lambda, that gives wavelength equals h over mc. You see, so you take a particle, you completely blow it up, convert it to light, and that light will have this wavelength. So if you were to convert a particle of mass m to a photon, it would have this wavelength. So that's the physical meaning of this thing that sits right here, and it's called Compton wavelength. Okay, so Compton effect demonstrated further that we should take seriously the idea of light being the particle, and it can explain the experiment in a way that classical notion of light as just a wave could not do. However, it's a funny description of a particle because it still has its wave aspects, frequency and wavelength in it. So again, we're encountering something called wave-particle duality. Okay, so that's enough for today. We'll continue more tomorrow. Thanks. Bye.